Hello guys, today we will talk about and work with the average nearest neighbor tool in ArcMap. So in GIS, average nearest neighbor analysis is used to evaluate spatial patterns of point data to see if features are clustered, randomly distributed, or dispersed. Average nearest neighbor tool calculates the average distance from each point to its nearest neighbor and compares it to the expected average distance if the points were randomly distributed across the same area. So resulting nearest neighbor ratio indicates spatial patterns. Values less than 1 suggest clustering, values around 1 indicate randomness, and values greater than 1 shows dispersion. So average nearest neighbor analysis in GIS is useful in applications like ecology, urban planning, and public safety. For example, it can help identify clusters of endangered species, assess accessibility of urban facilities, or detect crime hotspots. Most GIS software such as ArcGIS and QGIS includes tools or plugins to calculate average nearest neighbor, making it a valuable method for spatial pattern analysis in GIS projects. So let's go back to ArcMap. So this is our data sets. Calls for February 15, the start of the incidents. We can close this proposed stations. These are active stations. This is our area and this is our road. So let's imagine that we need to analyze. We need to make a special analysis. If we want to know the emergency medical services, this MES calls for this area have a tendency to cluster. If so, the government, for instance, might consider stationing emergency intensive care units at locations near the hotspots. So we will use this average nearest neighbor tool to analyze the data and determine the degree of clustering or dispersion. Ultimately, our goal is to decide whether or not to reject the following null hypothesis. This calls emergency medical service calls for in February 15 are randomly distributed across the study area. So average nearest neighbor tool is very sensitive to the area. Let's analyze the shape area. We'll be this analyzing for this area. Open attribute table. So this is a polygon. See, so this is a shape area. Let's let's copy it for. We will use it for the later analysis. Let's copy and we can paste it here. So let's close it. So let's go to the MES calls, go to properties, and there is a definition query here. So see that if we open, so these are the attributes. So incidents type larger than 300 and incident type smaller than 322 are just excluded from this analysis. We can go here. These are the lots of attributes here. The calls, this incident calls, which goes outside of our study area on this incident type. See this attribute, which goes outside our study area here, which might be here, just excluded from the analysis. So if you also want to exclude this, if you want to analyze for this area, for your certain area, for instance, you can exclude using definition query. It doesn't mean that it all completely deleted from the shape file. I can just delete this definition query, and all these dots will appear again here. So let's go to average nearest neighbor. So EMAS calls. So we're going to make analysis whether these calls are randomly distributed, dispersed, or clustered. So we'll use this. So first, let's go back and open again average nearest neighbor. So see that there is average near as short description calculates the nearest neighbor index based on the average distance from each feature to its nearest neighboring feature. So this is dispersed, this is clustered. And now we just need to copy and paste this our area, because we're going to analyze for this area. If you don't put the area, it might analyze to the whole extent of the file. So generate a report, yes. Let's click OK and let's wait. Let's go to we need to find these results. Go to geoprocessing results. So see that report file. We can go and open the report file here. So it gives us this kind of statistical analysis. So average nearest neighbor ratio 0.5, z-score minus 80, p-value is very high. So this is a clustered, very high, random, and this is dispersed. This random is dispersed. So given the z-score of minus 18, there is a less than 1% likelihood that this clustered pattern could be a result of a random chance. This means that there is 99% of probability that the calls are clustered. So average nearest neighbor summary, observed mean distance, expected mean distance, nearest neighbor ratio. We can go back to nearest neighbor ratio. Resulting nearest neighbor ratio indicates spatial pattern. Values less than 1 suggest clustering, while values around 1 indicate randomness, and values greater than 1 shows dispersion. So it shows nearest neighbor 0.84 means that the features trend towards clustering. The lower the index, the greater the probability that the data is exhibiting statistically significant clustering. So this score minus 18.8 with a significance level of 0. Very high. This score falls into the range that allows us to reject the null hypothesis. If the z-score was closer to 0, it would produce a confidence level that does not support rejecting the null hypothesis. So you must remember, the greater the z-score values, either in the positive or negative direction, given a higher confidence level that the distribution is exhibiting clustering or dispersion. So the z-score which we get gives 99% confidence that the data distribution is not due to random chance, which is the reverse of the statement in the dialog box. With high confidence level, we can safely reject the null hypothesis. So our null hypothesis was that calls for services, EMEA's call for services, are randomly distributed across the study area. So we can reject this null hypothesis, confidently saying that they are clustered rather than randomly. We can go back to this call, see that there is some clustering here. So these are clustering, so these calls are very close to each other. The same here, very close here. These are more random, but this area, see, these areas are very empty. These are also empty. These are also empty. If it would be randomly random calls, it would be very randomly distributed. Here, calls like this, dispersed, see that it will be evenly distributed throughout the whole area. But we see some clustering here, so there is a high level of confidence that the clustering exists. So you can see here also this results of this average nearest neighbor. So this is how this tool can be used. So other examples, for instance, a pizza chain might want to determine the clustering of its clients using the nearest neighbor index. The index will allow the company identify customers who are close to each other, more so than would occur at random, and perhaps categorize the cluster as a delivery hotspots. Another example, an epidemiologist might look for clusters of a certain illness and match the clusters to the locations of food sources or water to determine whether these other geographic elements are associated with an underlying cause, and also many real-life applications.